Okay, the time is 1 o'clock and we can start with the next speaker, Professor Zabeti from the University of Sistan and Baluchistan, Iran. And his talk is about the Banach-Saks property from an order point of view. Professor Zabeti, welcome. You can start.
Thank you, Nazif. Thank you. Hello from Zahedan, Iran, for everyone. And first of all, I would like to thank the organizer of the conference for giving me this opportunity to participate at this conference and to give a talk here. And it is my pleasure to see my friends and my colleague here online. It is really my pleasure. And I wish all of you and yours healthy in this difficult situation because of COVID-19 pandemic in the world. Okay, let me switch on the main topic of my talk, the Banach-Saks property. From an order point of view, I mean that the different notions of Banach-Saks property, which are defined in Banach lattices and in general locally solid vector lattices. The notion of Banach-Saks property is a noun notion in Banach space theory, but in Banach lattices, it is somehow not as older as the Banach space case, but we can obtain several somehow interesting results in this category as well. Just recall that the Banach space is said to have the Banach-Saks property, BSP for short, provided that for any bounded sequence Xn, there is a subsequence Xn of Xn, whose Cesaro means is convergent in norm, which means that this sum, Cesaro means, is norm convergent. For example, every reflexive Banach space has this property, but for sure, there are non-reflexive spaces which have this property as well. Also, X is said to have the weak Banach-Saks property, WBSP for short, if every weakly node sequence Xn has a subsequence, which Cesaro means is also convergent in norm. And in this case, it is easy to see that the Cesaro mean is also 0. For example, L1 possesses weak Banach-Saks property, but it fails to have Banach-Saks property. But always, Banach-Saks property implies weak Banach-Saks property by the definition. These two notions have been investigated in Banach spaces for several decades. Now let us switch on the Banach lattice theory. The most important difference, undoubtedly, is the order between the Banach lattice and Banach space. And this ability and order helps us to establish some powerful and more interesting results. For example, we know that the Banach space is reflexive if and only if the Ischelous unit ball is weakly compact. But in Banach lattice case, we have another characterization. We say that the Banach lattice E is reflexive if and only if both E and E' are KB spaces. By a KB space, contrary which Banach space, I mean a Banach lattice in which every non-bounded increasing sequence is convergent. So there is another characterization with using order in reflexivity of Banach lattice. So it is natural to expect some order aspects for the Banach-Saks property while we are dealing with Banach lattices and also in locally solid vector lattices. So one distinguishable part which comes to the mind readily is using disjointness. In a vector lattice, we say that two vectors X and Y are disjoint if the modulus of X and modulus of Y are 0. If you want. So two related notions have been considered in this direction and investigated for several years. On the other hand, recently, unbounded absolute wave convergence, or UAW convergence in brief, as an unbounded version of wave convergence and also absolute wave convergence has been investigated. In particular, this topological convergence enables us to characterize order continuity being KB space and reflexivity of Banach lattice in terms of UAW convergent sequences. Furthermore, recently, there has been an effort to transfer some known result in Banach lattice theory using wave convergence to the unbounded version by replacing wave convergence with the UAW convergence. For example, recently there have been some efforts, UAW Danforth-Bethe operators, unbounded continuous operators, para-unbounded continuous operators, and so on. There are some papers in the references that we shall see about them. Now let me explain some about the unbounded convergence here. The concept of UN convergence, introduced by Troitsky at first in 2004 and further investigated recently, suppose E is a Banach lattice, a net of X alpha it is called unbounded non-convergent, UN convergent in brief, to X if the norm of modulus of X alpha minus X inf of U tends to 0 for every positive U belongs to E. The notion of UAW convergence, considered and investigated in 2018 by me, a net of X alpha in a Banach lattice is called unbounded absolute weight convergent or UAW convergent to X if the modulus of X alpha minus X inf of U tends to 0 weakly for every positive U belongs to E. Both UN convergence and UAW convergence are topological. This notion agree together if and only if the underlying Banach lattice is order continuous. So there is another characterization of order continuity of Banach lattice using these unbounded convergences. Now, let me explain more about Banach-Saks property. Suppose E is a Banach lattice, E is said to have the unbounded Banach-Saks property, UBSP for short, if every non-bounded UAW nor sequence Xn has a subsequence Xn whose Cesaro means is conversion in norm of a Banach lattice. Also, E possesses the disjunct Banach-Saks property, DBSP for short, if every bounded disjunct sequence in E has a Cesaro conversion subsequence. And E has a disjunct weak Banach-Saks property, or DWBSP in brief, if every disjunct weakly nor sequence in E has a Cesaro conversion subsequence. When E is a Banach lattice, like Banach space, weak Banach-Saks property and Banach-Saks property are defined similarly, such as Banach space. As you see, in a Banach space, we have two notions for Banach-Saks property. But in a Banach lattice, we have four notions here, and four of them uses order. These two notions, disjoint Banach-Saks property and disjoint weak Banach-Saks property, have been investigated and defined before, but this definition is recently defined by me, and some result has been investigated, in particular relation between this kind of Banach-Saks property and other kinds. For example, suppose E print the dual of E's order continuous. If E possesses weak Banach-Saks property, then it satisfies unbounded Banach-Saks property. Unbounded Banach-Saks property always implies disjoint Banach-Saks property. And when E is an AM space or an atomic order continuous Banach lattice, unbounded Banach-Saks property implies weak Banach-Saks property. Also, every AM space possesses disjoint Banach-Saks property automatically. For a Banach lattice, we saw that unbounded Banach-Saks property implies disjoint Banach-Saks property according to this lemma always. For the converse, we have that in order continuous Banach lattices, this notion agree. I mean that the sigma order complete Banach lattice with disjoint Banach-Saks property possesses unbounded Banach-Saks property if and only if it does not possess a lattice copy of infinity. In other words, if and only if E is order continuous. A Banach lattice with weak Banach-Saks property possesses unbounded Banach-Saks property if and only if it contains no lattice copy of L1. In other words, dual if is order continuous. Also, we have this result, corollary, a sigma order complete Banach lattice with disjoint weak Banach-Saks property possesses unbounded Banach-Saks property if and only if it does not possess a lattice copy of either L1 or infinity, both of them. In other words, the norm of E and the norm of dual of E, if Brinner order continuous. Recall that when E is an atomic KB space, every bounded sequence, non-bounded sequence in E has a UAW convergence subsequence. It is shown that in the previous papers. So we have the following. Suppose E is an atomic KB space which possesses unbounded Banach-Saks property. Then it also satisfies Banach-Saks property. It's similar to reflexivity plus atomic. Okay, now let me switch on the locally solid vector lattice case. The following notion, unbounded convergent in topology, has been introduced and investigated by Taylor and also Emilianus and some others here. Suppose x and 2 is a locally solid vector lattice. Nth of x alpha subset of x is said to be unbounded convergent to x belonging to x. In brief, x alpha tends to x u2. If for each u belongs to x positive, the modulus of x alpha minus x inf of u as a net converges to 0 in the two topology. Suppose TO1 is the norm topology and TO2 is the absolute wave topology. Both of them are locally solid topology. Then x alpha tends to x in un and x alpha tends to x in uaw respectively. So this notion, unbounded convergent in topology locally solid, is an extension and generalization of the un convergence and uaw convergence. So this is an extension of the previous result in the topological setting. Now we have defined some notions of Banach-Saks property in locally solid vector lattices. Suppose x and 2 is a locally solid vector lattice. X is said to have the Banach-Saks property. For short, we say the locally solid Banach-Saks property because we want to be different with the Banach lattice case. If every two-bounded sequence xn of x has a subsequence xnk, whose Cesaro means is two converges in the topology of two. That is, 1 and sigma k from 1 to n xnk is two converge. The strong unbounded Banach-Saks property, locally solid strong unbounded Banach-Saks property notation, if every two-bounded utonal sequence has a subsequence xnk whose Cesaro means is two convergent as well. Unbounded Banach-Saks property, locally solid unbounded Banach-Saks property notation, every two-bounded unbounded absolute null sequence. I mean that when we have a two topology, we have an absolute vector topology here. So unbounded with respect to the absolute topology has a subsequence xnk whose Cesaro means is to converge. And also disjoint Banach-Saks property here, if every two-bounded disjoint sequence xn of x has a subsequence whose Cesaro means is to converge. Note that we have two notions here because when we are, for example, two topologies, the norm topology here means that un null sequence, and here means that uaw sequence. So we have two different notions. Of course, for example, in order continuous Banach lattices of locally solid vector lattices per Lebesgue property, they may coincide together, but in general, they are different. So we use two different options for them. No, as you remember here, we proved we had a lemma, which is simple lemma, but interesting that every AM space possesses a disjoint Banach-Saks property. We are looking for such lemma in locally solid vector lattices. For here, disjoint Banach-Saks property locally solid vector lattice. But the problem is that the AM space is depend on the norm structure. We have a norm structure here by the definition of a AM space. Okay. So, but there are many locally solid vector lattices that don't have any norm structure. So, when we are looking for such a lemma and such a result, we should look carefully for some conditions which does not depend on the norm. It depends on the topology. As we see more, we see that by the definition of AM space, the finite suprema of elements in the closed unit ball are also bounded, and more precisely, they lie in the closed unit ball again. For example, if we have 100 elements here in the closed unit ball AM space, the finite suprema, again, the norm is less than or equal to 1. 100 element, their suprema, lies in the closed unit ball again. So this motivates us to define the following fruitful observation here. First, we have this. Suppose it's an Archimedean vector lattice for every subset of X by A sub. We mean the set of all finite suprema of elements of A. More precisely, A sub equal to A1 sub of n belong to the natural number and I belong to A. So let me switch on the definition because the time. Suppose X is a locally solid vector lattice. We say that X has the AM property, provided that for every bounded set B subset of X, B sub is also bounded with the same scalar. Namely, given a zero neighborhood V and any positive scalar alpha with B subset of alpha V, we have B sub also subset of alpha V with the same scalar. Like here, because the kilos unit ball, I mean that if the norm x1, x2, x10 less than or equal to 1, then the norm of final suprema is also less than or equal to 1, not 2, not 3. Okay. So now AM property is the right extension for the AM spaces. I mean, we have this theorem. Suppose E is a Banach lattice, then E is an AM space if and only if it possesses the AM properties. So this definition in Banach lattices are the same. So this is a real exception for this, but in locally solid vector lattice. We have a lemma here. Suppose E is a locally solid vector lattice with the AM property, and U is an arbitrary solid zero neighborhood. Then for each M belonging to the natural number, the finite suprema of U equal to U, in which U is a period M times 2, 3, 10s, 1,000, and any finite number. Now we use this lemma to prove this similar result to the Banach lattice case. Suppose X is a locally solid vector lattice with the AM property, then X possesses the disjoint Banach-Saks property in the sense of the locally solid vector lattices. Moreover, we have another similar result. Suppose X is a sigma order completely locally solid vector lattice, then unbounded Banach-Saks property in X always implies disjoint Banach-Saks property. And for the converse, we have this. Suppose X and 2 is a sigma order completely locally convex solid vector lattice, which is also a Frege space, a metrizable, complete metrizable space. Then disjoint Banach-Saks property results unbounded Banach-Saks property in X if and only if X does not contain lattice copy of infinity. In other words, if and only if X possesses the parallel property. So this is similar to the order continuity case in Banach lattice case. Just we had Banach space and norm here, not metrizable. And also, it is clear that unbounded Banach-Saks property implies that a strong unbounded Banach-Saks property, because the strong convergence implies that weak convergence. But for the converse, we have another characterization here. Suppose X and 2 is a sigma order completely locally convex solid vector lattice, then a strong unbounded Banach-Saks property in X implies unbounded Banach-Saks property if and only if X does not contain lattice copy of infinity again. And two final result is that suppose a topologically complete locally convex solid vector lattice possesses Banach-Saks property, then X and 2 possesses the Lebesgue and Levy property. These two notions are similar to being a KB space in Banach lattice case. Converse, suppose X2 is an atomic locally solid vector lattice which possesses the Lebesgue and Levy property, then a strong unbounded Banach-Saks property in X implies Banach-Saks property here. So another relation between them using possess Lebesgue and Levy property. Now, let me explain in 2 minutes. I think we have 2 minutes here about references. There are 3 nice papers by Gao, Zantos, and Troitsky about UO convergence and different application of it. Very nice paper, especially the last one. It is very nice in Banach-Saks property. The last one, and also the second one. Also, there is a paper about the UN convergence here by Troitsky and Ding O'Brien. Nice paper. There is a paper by Nazife and Anil and me about operators in locally solid vector lattices here. Also, there is another paper about UN topology in Banach lattices by Marabe, Troitsky, and Kandik. Good paper. The other paper, I think maybe they are not so good as the previous one, but by me, this paper is about the AM property that I introduced briefly here in general, and some application of it its relation with Lebesgue property and some related ones. Here is the Banach-Saks property for in locally solid vector lattices here, and also another paper about unbounded continuous operator and unbounded Banach-Saks property in Banach lattices you can use. Thank you so much for your attention here. If you have any questions, please don't hesitate to ask here and by email to me. Thank you so much.
Thank you very much, Omid, for an interesting talk. As he said, are there any questions or comments?
As I expected, I have a question. So,
please.
Yes, sure.
For the notion of, there is many notion of unbounded norm, unbounded weak, and unbounded with respect to topology.
Yes.
And my question, for example, for Banach-Saks property, sometimes yes, when we go to more general situation, it is possible that proofs get easier. Is it the case here?
It depends on the situation, I think, but you're almost right, because here, for example, when we are dealing with Banach lattice case, we have more options to work with. For example, we have norm, we have order continuity, we have many theorems about order continuity being KBS based, many characterization of KBS based reflexive spaces, order continuity, and so on. But when we are looking for locally solid vector lattices, we don't have many theorems in this direction. So we lose many tools here. So it can be somehow more difficult to work. But of course, in Banach lattice case, because many others are working, so working in a research project is harder, in my opinion, with respect to the locally solid or topology case, because less people work in the topological case, for example.
And what about operators? There is some notion of Banach-Saks operators. Are there generalized?
Honestly, I have not thought until now about them, because I thought it is really similar to the just proper Banach-Saks property. Just we should transfer some result here between the space and the operator space. But here, in these references about unbounded continuous operators, I try to characterize reflexive spaces, KBS spaces, and reflexive spaces in terms of operators here. If you were interested, I can send the paper for you to read it if you are interested.
Yes, okay, thank you, yes.
For sure.
Any other questions? Okay, let us thank the speaker again. And thank you very much, Omid. And
You're
time,
most welcome.
we have 7 minutes more for a break. And we will start at 2:30. Could you please?
Thank you.
Yep. Omid, could you please stop the share?
Yes, sure.
And Professor Hantos, you can start to share your screen.
Thank you.
Hi, Foyves. How are you?
Thanks for the talk, Zabeti. Thanks for the talk.